two parts of your question. Yeah, Bob?
Yeah, I may be able to shed a little light on that point stuff. When you do a electrostatic plot of that sharp point, you know, you plot the field,
right.
Then the gradient is much more concentrated at that point, at the sharp point. For example, when you have lightning rods, the charge leaks off a sharpened point, etc. So the sharpened points get the attractors. Okay, and that's the simple physics.
Yeah.
Because there's a larger gradient. There's a larger gradient potential difference. There are more force lines coming off of that point than on the sides. More? Okay? So it's a higher gradient coming off the point than it is off the sides. So there are less lines on the sides and more lines to the point, so that's an attractor.
Yeah. There's considerably other factors involved in that tiny little phenomena. For instance, when the water evaporates, that spot gets cool, but it has to be warm for the evaporation to take place. So you get an emission or radiation, and then we get the contraction of the lowering of the temperature. So there's a very intricate thing going on here, and we need to spend a lot more time trying to figure it out. Oh, this gentleman here has a question, Bob, right in front row.
Just simply an explanation of the square wave, maybe an instrument compatible, or not compatible, comparable instrument to a square wave producing. You had brass for the trombones, and the clarinet was wood.
Drum is a pulse wave. Drum is a pulse wave. Percussion is a pulse type deal, where it's kind of like this, only it's more compact and pulled together, right? That would be a percussion. I'm trying to run through my mind. The xylophone keeps coming to mind, but I'm not sure that's accurate.
Well, yeah, in CD players and stuff like that, the reproduction is square wave, and there's a couple articles on how people don't feel as harmonic with that after it has been produced that way.
There's why
subconsciously.
Right. There's two reasons why that takes place. Probably a whole lot more. Two I know of. First place in digital sampling, when they sample the music and put it on the discs. The sampling technique is the microphone or the sensing device will listen to the music and then stop, and listen to the music and stop, and listen to the music and stop. So that's sampling, and so many times a second. Generally, it's around, I think, 30,000 times a second. Well, what happens between those samplings is lost. But because our ears only react so quickly, we don't really hear that, but people who are trained in music, who are very sensitive, can pick that up, and it is not correct music. So the digitally reproduced music is not analog, it's digital, and all that, those high harmonics, like we're talking here, we go from the high harmonics, even though we aren't aware that we hear them, our body reacts to those. So if a computer samples it and leaves those out, we don't get that. See, we don't get that at all. It's not there. And the other factor is the square wave, as we've seen, it's aliquot constructs that create it for what it is. It doesn't have all the other components. So all digital, or nearly all of it, is done with square waves. So there again, we've got a distortion of what the natural phenomena is. And we've got an artificial phenomenon. So computer music is artificial, period. So getting back to this triune waveform. Longitudinal wave is a wave that goes out away from its source. It's going straight out away from its source. So we've got, in this particular design, the longitudinal is up and down. So it's straight out, and going the backwards too, the same thing. But it goes out and it comes back, out and it comes back. That's one direction. The transverse or shear wave, a lot of these vibrations have different names. These are the technical scientific terms. The transverse or shear wave is 90 degrees to that. So as longitudinal goes out, the transverse is like this. It goes out on this plane. And we can say longitudinal goes up and down like I'm standing, and longitudinal is up and down, and the transverse is on this plane. So if I rotate it, it'd still be on this plane. That's the transverse going out. That's the ripples on the water. Okay? The Raleigh wave, now all these things are 90 degrees to each other. So we've got one up and down, and one this way that's 90 degrees to the first, The Raleigh wave is 90 degrees to those, and it spins like this. It rotates. It has a curvilinear momentum to it. And it may be a result of the first two adding together in some sort of way to create this vortexian motion. So we get a tornado going, or a hurricane, we have evidence of all three vibrations going on at the same time. And Keely made these motors, these negative attractive things. One of the most amazing things he ever made was what he called his musical sphere. And there are these big brass and copper spheres. He made some out of glass. I think his original first ones were made out of glass. And he would play a tune on his harmonica or whatever, and these things would start to spin. He understood this triune mechanism of the vibrations. Once the thing got to spinning, it would spin faster and faster and faster until the thing would destruct itself. But he would play a different tone and disrupt that chord of vibrations going on inside the sphere, and it would stop. And he always liked to hand somebody one of these spheres when they came in, and he'd get it to spinning, and it would go so fast these people would be terrified holding this thing. And he would eventually, he would act like he couldn't get it stopped, see, and then he would eventually stop it. But those musical spheres, I've been real curious about how and why they work. I've got 3 different experiments I've done that cause rotation that conventional science, to my knowledge, does not explain what's happening. And I want to understand rotation. Keely left us a chart and on what causes rotation. It's a musical chart. It's full of musical notations and whatnot. We don't yet understand that. But in these 3 experiments, one was done with a radiometer. And a radiometer is just a small little, looks like a light bulb, and you put it in a light on your windowsill and the thing will spin. Looks like a little windmill. Conventional engineering has about 6 different definitions of why that does what it does. And I think they're all wrong, because if they were right, we'd only have one explanation. And Keely said that if you vibrate an atomic substance with an atomic vibration, you get rotation. This was the first experiment I did to prove to myself that Keely was not bogus, and I wasn't going to waste the rest of my life working with him. And I said, okay, well, let's do this experiment. So I had a radiometer, and most people don't realize this, but a radiometer has argon gas in it. If you take the argon gas out, it won't rotate. So the argon gas, to my interpretation of Keely's work, is an atomic substance. It's not a molecule, it's not a complex atom, it is an atom of argon. You know, in this case, a lot of them. And the only source of vibration I had to me at the time was my microwave oven. So I just took this radiometer and put it in my microwave and turned it on. And I'll tell you something. If you want to be excited, you try it. This thing, the bulb itself began to flash. Brilliant white flashes like you see on flash bulbs on cameras. This thing will flash so brilliant it'll blind you. And then this thing started to spin, but it didn't just start to spin. It span so fast you couldn't see it. It just became a blur, just like that, instant. But you got to be careful. If you leave it in there more than 3 or 4 seconds, the needle that suspends the little windmill turns red hot, white hot, and it melts right through the little glass thing. So in 5 seconds, it costs you $10. That's about what those things cost. So you just want to run it 3 or 4 seconds and see this thing. It is absolutely incredible. And that taught me 2 things. One is conventional engineering knows nothing about what causes those things to do what they do. They don't know anything about it. And 2, Keely knew. Unless it was just a bunch of circumstances that happily resulted in all this motion and activity going on in this microwave. Another experiment I had, and I brought it with me. It's over here on the table, and I'll show it to anybody who wants to see it. We took a armature from an electric motor, and we stripped all the copper wire off of it. There's no magnets on it. We put 2 bearings on the shaft, and if you attach a DC current to either side of this armature and give it a little nudge, this thing will start to spin, and it will accelerate until it flies apart, but it gets too hot for that. We disconnect it.